Hello everyone. In this lecture, we are going to discuss about the functional completeness of multiplexers. There are multiple types of multiplexers, which I have talked about in the previous lecture. So there are 2 cross 1, 4 cross 1, 8 cross 1, and so on, 2 to the power n cross 1 multiplexers. In one of my lecture, I have also talked about the functional completeness, and we have also proved that NAND and NOR gate are functionally complete. That's why we can utilize NAND and NOR gate to realize any kind of circuit. So in case mux are also functionally complete, mux can also be utilized to realize any kind of circuit. So let's take an example and try to understand. Let's say I'm taking one multiplexer which is 2 cross 1. Now we have already discussed that in 2 cross 1 multiplexer there will be one select line. So let's say I'm taking select line here. This is the select line, and there are two input lines and the output. Enable line is there, so I'm not drawing the enable line, right? So we assume that circuit is already enabled, right? So this is 2 cross 1 mux. Okay, this is I'm considering, let's say I0, I1 input, and this is, let's say, S0 select line, and this is Y. Now I have already told you that this Y will have the expression like S0 bar I0 plus S0 I1, right? So this thing we have already talked about. Now let's test the functional completeness. So if this function is functionally complete, first thing, it must be capable to generate the complement. Okay, so let's say if I want to generate the complement of a variable a, so I want to generate, let's say, a bar. So first we need to check whether this Boolean expression anyhow can we convert into a bar or not. Now when you look at it, I0 and I1 we cannot convert into complement because these are given as positive. There is no complement on I0 and I bar. Similarly S0 here. So if you want to get complement of anything, we can get with the help of S0 bar, right? So that means that A we need to pass here, right? Which I want to complement, that need to be given by select line, right? Now, so if you realize S0 is A, it will give you A bar. So in case I want A bar in this format, how I can convert? I can write A bar. Now here it is I0, so because I want only A bar, so I can write A bar dot 1. And in this form, if I want to convert the A bar, there is, let's say, S0. So S0, because I'm passing S0 as A, so I would say this is A. And I1, because I don't want anything here, I want only A bar, so I will pass I1 as 0. So if I write this thing, this is equivalent to A bar only, right? So you can get out of this A bar, you can convert. So I'm concluding that Y can generate A bar if you can say I0 is equal to 1 and S0 you are passing as A and I1 is equal to 0. I hope you are getting it. So in this mux, if you are passing A here and I0 is you are passing as 1, and I1 you are passing as 0, in that case Y will give you A bar. Okay, so it can generate complement, multiplexer can generate complement, there is no problem. Now let's test the same thing for whether we can generate the OR operation or AND operation. So let me clear this. Now the same thing we can try for AND and OR. So if you recall the truth table of AND, the truth table of AND, in case of there are two variables involved, it look like this. So let's say you are having A and you are having B, and you are intended to generate AB or A dot B, then in that case there will be four combinations. So 0, 0, 1, 1, and there will be 0, 1, 0, 1, right? Right? Now here, when you generate this, so this will give you 0, this will give you 0, this will give you 0, and this will give us 1 only, right? 1 and 1 will give us 1, right? So if we want to represent our function y, let's say in terms of AB, we can write like in this manner. Okay, now if we want both the things without any complement, that means this portion, if we compare, this will not give because there is a complemented one. So in case, instead of S, if we pass A, and instead of I1 if we pass B, this thing can give us A dot B. I hope you are understanding. So what I'm saying here is, you try to understand, if I'm passing here A, and instead of I1 I'm passing here B. Now what about I0? I0 I'm making as 0. So if I'm making I0 as 0, in that case, if I write it in the same manner, so you will get here S0 instead of S0 we are getting A bar, because S0 is, we are passing A, dot I0 is 0, so this portion will be eliminated. S0 is A, dot I1 is B. So in that way this Y will be capable enough to generate AB, right? So it will be generating AB if you can say S0 is equivalent to A, S0 is equivalent to A, I0 you are passing as 0, and I1 you are passing as B. In that case A and B can be generated. So that means this mux is capable enough to generate complement, and it can also generate AND operation. Now if you want to test for OR operation also, let's look at it. So whether mux can generate OR operation in order to claim the functional completeness, let's look at that also. So let's say I'm cleaning this. Now I'm cleaning this also, and here I'm interested to get A or B, right? So if you look at the truth table, 0 0 will give us 0, and this will give us 1, this will give us 1, and this will also give us 1. So this is A or B. Now if we want A or B generated here as Y, so if we want it, then in that case Y can be written in these terms. So this is A bar B, because this truth table is representing A or B. So in case we want to generate A or B instead of this here, instead of Y, then how it will get? There are three possibilities where we can get this thing as one. So you will get A, B bar or AB, right? So according to this truth table, we can get A or B in these three places, right? So here it is A bar B or A B bar or A B, right? Now we can solve it. So in case we take B as common, in these two terms there is one thing, that is B, which is common. So let's take it common. So if you take it, then in that case, let's say this term is left. So I'm writing A B bar plus, here it will become B A bar plus A. So it will become A B bar plus B, right? So this thing we need to compare with the function of mux. Now in order to compare, we need one bar and one variable which is not having bar. So if B is having bar, this thing I'm assuming this is 1, right? A bar plus A will give you 1. So I'm writing 1 so that there'll be the similar format it will look like. So I'm writing something like this: B bar dot A. I can write A B bar like B bar dot A, commutative law, right? And here I'm writing B dot 1. So now if you compare, look at very clearly. So if I compare, let's say instead of S0, I am passing B. So if you pass instead of S0 B, it will become B bar here. So this is B bar. And instead of I0, if you are passing A, so this will give you B bar A like this, right? And because already S0 is equal to B, so this will give, now this is I1. So instead of I1, we are passing 1. So with this, if we pass, this will realize or behave like A plus B. I hope you are getting it. I hope you are getting it, because this Boolean function is representing A or B, right? So that means we can conclude that this mux is functionally complete. It is capable to generate complement, it is capable to generate AND, and it is also capable to generate OR operation, right? So we can utilize the mux for realizing any kind of circuit. So we will solve few problems in the coming lectures. Thank you.